Thanks, Hani, and thanks for inviting me. I'm very happy to be here the first time at IPAM. As Hani said, I'm a university professor of the Technical University of my state, Rhineland-Palatinate, and I'm head of a Fraunhofer Institute, which is the only Fraunhofer Institute for mathematics, applied mathematics. And I'm going to talk about mathematical models in public transportation. So I try to relate them a little bit to equity constraints, and I'm very eager to learn more about equity and how we can make use of that. But whenever we want to do something, I think it's a good idea that all of us know what is already here, and that's what I want to show. So I have one large chapter 1 where I go through the stages of public transport planning and show you models and algorithms which are already available. And I have a shorter section in the end for the last 10 minutes or so where I put together some remarks on equity. I also will have some remarks on equity after each of these subsections. If you have any questions or comments, I'm happy that if you interrupt me. So what is the general goal in public transport planning? And as a mathematician, we always like to have a clearly defined problem. So under a restricted budget, we want to make public transport as good as possible. And as you see, I have marked good in blue because good is now a matter of definition, what we think is good. And there are many different objectives. So whatever you find in most papers, you will have this general goal under a restricted budget, make public transport as good as possible. That is nearly in all papers the general goal. Now, what is good? Good means that we want to have to minimize the traveling time for a given demand. So first of all, what is traveling time? Traveling time is the time you spend in the public transport system when you boarded the first bus until you leave it. And perceived traveling times means that we need not only count minutes, but there are some people who say that we would like to add a penalty for every transfer and things like that to make it a bit more realistic to the utility somebody really has. And then we also have this given demand. So usually we have given some origin-destination matrix from where passengers would like to travel, and we take this as granted and optimize for such a demand. And this demand often excludes people who cannot be served. So if we get the first demand matrix and should do something like optimizing the lines or whatever, this matrix is only describing people that have access to the system, except of the first step. So we will see that in a minute. So why has this developed? And this is maybe important to understand also for my last slides. From a historic point of view, the idea was that public transport should provide accessibility to everybody, like school kids, people who do not own a car, people who do not have a driving license. Everybody should be able to go to have some kind of mobility, which fits very well to the first talk of Karel we had this morning. And this was, I think, the first idea, how to provide sufficient accessibility to everybody. And also research on public transport optimization started maybe in the 70s. It had a lot of people working on that already in the 80s. And there also environmental goals like pollution was an issue, and people looked at that. Yeah.
One small question. What is good perceived traveling time? Do you include access and egress time, or it's typically not included?
Depends on the author. Sometimes included, sometimes not. Depends on the problem. In timetabling, you would not include it, for example, but for frequency setting, you include often waiting time at stations. Yeah. Also not a completely clear definition. Everybody defines it a bit differently. Okay, and now we want to go to look through these steps. Usually public transport planning comes in several stages. I start with the infrastructure. Where should stops or stations be located? Here we come also to the question, can we serve everybody? Then we find lines and their frequencies. Then the timetable is set. And then I put it into two different branches because the vehicle schedules, or for railways, you would call it rolling stock planning, that is something which is important for a limited budget because that is a driver of the costs, but the passengers do not see that. So it's only important for estimating the costs and also the crew schedules. But the passengers also see the tariff system, and in this position, if you have disturbances and want to deal with them, that's also again important for the passengers. I want to add a note on integration, our goals that we have to have a good traveling time, efficient transport system under a limited budget, would work better if we would not solve this step by step in a sequential way. That is just like a greedy heuristic. But if we could do it in an integrated way, and in a big research project, we integrated these 3 steps and could show that if we are able to solve them together, we can get significantly better results. But I could talk about maybe 2 days about just this integration issue. I'm not doing that today, but I just want to mention it. Okay, also literature is numerous and still increasing. Not only lots of research papers, also books on public transport planning, public transport optimization. And what I can do today is just to give a short overview on the basic models for each of these steps and stages. And at the moment, I'm also writing an article together with Mark Hickman up for the 50 years of operations research special issue of Euro. And maybe we also happen to summarize this in a good way there. Before I really start, I have one commercial break for you, which goes about a software package we are developing at my place in Kaiserslautern, and formerly I was in Göttingen. I started already there, which is an open source library for public transport planning. And it's called LinTim. Lin comes from line planning and Tim from timetabling. But it also includes stop location, vehicle schedules, tariffs, and even delay management. You can download that freely and work with that. It's open source. Here is again all the stages that are here, and it comes together with some data sets which are also open source that you can use. Some toy examples, some bus networks, a metro in Essence, and the long distance railway in Germany or related to them. And we continuously add more and more data to it. This is our team last year. We had the 15th birthday of LinTim that we celebrated. We have also users in Switzerland, in India, in Sweden. And now Feline took the thing with her to, she's my postdoc at this stage, and she's changed to Helsinki in Finland. And she is now head of LinTim, but these 3 people are together if you have any questions. So don't forget LinTim, and this is the end of my commercial break. Okay, now let's start with stops and stations. That is a rather old problem, and the idea is that you have given some demand points that are the squares here, like schools or leisure centers or hospitals. And what you would like to do, you might have also some tracks, railway tracks, for example, lying in the ground. And the question is, where would you like to locate stations? And in literature, you usually have the goal that you would like to cover as much demand as possible, and a demand point like this one is said to be covered if it is within a certain distance around the next railway station. The distance is in bus transportation often 400 meters, in railway they say 2 kilometers. So the question is where to locate the stops such that the number of stops is minimal and everybody is covered. This can be easily modeled as integer program. It is a covering problem, more or less. You have variables xi that indicate if a location is chosen as a new stop and 0 otherwise, at least if you have a discrete version where you have possible locations for the stops already given in a finite set. If you have just the tracks here, then it might have sense to be allowed to locate the stop anywhere on the track. Then you have a continuous version, but it is possible to reduce it to a finite candidate set such that you can use, again, the discrete version. The objective function in this classical problem minimizes the sum of the costs of the new stops, and the constraints is to cover all the passengers. So you can model it, as I said, easily as integer program, where you have the decision variables, choose a stop or not, you add the costs, and this is a covering constraint with a covering matrix, which indicates if a stop covers a demand point or not. Yeah.
So I'm a little surprised. I would say you make cost maybe a constraint and serving passengers as good as possible your goal. If you turn it around.
Yeah, here it is turned around. It is a kind of, I will come on the next slide, where we checked it, but this is a thing that was in the literature and what is used by many people. But I have come to the next objectives on the next slide. So first of all, even this simply to write down problem is NP-hard in general. It is nicely polynomially solvable if you have just a straight line and want to locate things here, then it can be solved by dynamic programming. And yeah, it is a covering problem. And has been emerged in location theory. And here is now the other objective functions we also worked with. You could also turn it around, which would be the usual thing in public transport, very, very correctly that you mentioned that given a budget, we want to cover as many passengers or potential passengers as possible. So again, in this radius I've said, and this has also been investigated by different people and also by ourselves. Or you could also say you have given a budget and you want to minimize the average access time. So that would be a typical objective in location theory. And what we also did with a very interesting project is to look at the door-to-door traveling time. This means we have, on one hand, the time the people need to get to closest station, but on the other hand, we also took into consideration that if you stop and go and stop and go, for every stop you lose 2 minutes. And this together was an approximation of this door-to-door traveling time, so the average. And we tried to minimize that in a project which was very interesting because it was a real-world project with Deutsche Bahn, German Railway. At the moment, they have around 6,000 stations in regional transport. And they asked the question, what would happen if we add, let's say, 3,000 new stations? That would be a density per kilometer of track as it is in Switzerland. And the question was, what would we benefit if we do it as dense as they do it in Switzerland? And the answer was yes, but only if you choose the right locations. If you have a lot of stations on high traffic tracks, then it does not pay off because many people lose a lot of time. Yeah.
So I'm a little surprised that you mentioned in the context of this very practical setting the NP completeness, because I would have understood from the kind of structure that these are very simple integer programs that can be solved by off-the-shelf software. And do you have any experience that indicates that that's not the case?
It depends on the size of the problem. So it is definitely NP hard is not NP hard. For some problems, you can solve it easily.
I guess I was asking, have you encountered a scale of problem where it isn't immediately solvable? That's
For the stop location now? Yeah. So for the door-to-door traveling time, we did not solve it exactly. We used a genetic algorithm to solve it in the end. That is, and it would not be solvable exactly in
what's this order of magnitude of sort of dimension of the problem for that?
Dimension to what?
The dimension of the problem.
The dimension. Yeah, we have 3,000 new stations, and we had like demand points. What was in a sales structure like 10,000 demand points, something like that.
And Garobi really couldn't handle this.
The problem is that with door-to-door traveling time is not so easy to model. In the covering problem, it would probably now be possible, yeah. But this was another objective function. And for the covering problem, it depends very much on the structure. So if you have a rather easy constraint matrix, like it has nearly consecutive ones property, things like that, it can be solved very easily. If it's a very, and usually in practice it has. So in practice it works more or less. But if you have just any structure, it gets hard. Okay, what about equity for stop location? One thing is that we want to cover all potential passengers, or as many as possible, which is somehow justice in accessibility. So that goes in the right direction to equity, I think. One could maybe better focus on people that have to rely on public transport, so on people that have no car or no access to a car, no driving license, school kids or so. And I think nobody considered the door-to-door traveling time under equity aspect so far, but you could also do that and try to optimize that. We will see a similar objective later on. Stops. I only can give a brief thing about each of them. I now come to the line planning. So what is line planning about? Line planning is also a bit of a covering problem. Here we have a network, a street network, and assuming one would like to cover all the edges by lines. So then we could establish a red line, and you could establish a blue one, and a green one, and maybe even a pink one. Now everything is covered, and this would be something we call a line plan. In this section, we not only look for the lines, but also for the frequencies of the lines. And for example, the blue line has a frequency of 4, meaning that if you have a planning period of 1 hour, it goes every 15 minutes. And the green line here has only a frequency of 1, so it only goes once per hour. So we want to determine the lines and their frequencies. And line planning is, in my opinion, the stage which has the most diverse literature. And why is this the case? First of all, we have many different models. So looking back at what we want to do in public transport, we want to optimize the budget and the traveling time, or restrict the budget and optimize the traveling time, whatever. But neither the costs nor the traveling time can really be computed in the stage of line planning, because to compute the real traveling time, we need to have a timetable, and to compute the real costs, we need to have a vehicle schedule, how many buses do we need, how many kilometers do they drive, how many crew is necessary. So many authors have many different assumptions how we can approximate these goals already in the line planning stage, and this is one reason why we have so many different models for line planning. These problems even have different names. In the more algorithmic and mathematical community, it's called line planning. But in the engineering community, as we heard also this morning, it's called transit network design problem. And both communities do very similar things, but under different names. So you always have to look for both things. And then it's done with or without frequency setting and different things. And also we have many different algorithms, also depending on the community. Engineers more or less go like a heuristic, practical way. Mathematicians define first the problem and then try to solve it exactly. So there's a very diverse literature on this topic. The first paper I'm aware of is from PATS, and I just want to mention that Ralph, who is in the audience here, also did a lot of good papers on line planning. I collected also some surveys for you, and this one is not finished yet, but at the moment we are writing also on a survey about this. So what is line planning about? We first have given this public transport network, I've shown you in this picture, which is a graph with stops and direct connections, and we have a planning period. And then a line is defined as a path in the public transport network. Every path in the network could be established as a line. The frequency says how often service is offered, and the line plan together with the frequencies is then what we call a line concept. So what we want to do is we want to find the lines, and this means we want to determine the number of lines, the routes they have, and their frequencies. That is what we want to have as outcome. And also this can be modeled as a very nicely solvable integer program, although it is NP-hard. So we have a line pool, and if the line pool is already given, here it's the line pool and it's given, then we can have again just some decision variables telling us if we take this line or not, if we have potential lines collected. Or even better, we just determine the frequency of each of the lines, and if the frequency is 0, then the line is certainly not established. It would even be better to have not a given line pool, because finding a good line pool is a problem for itself, but to integrate this and construct the lines on the way while we solve this problem. So from scratch, it would be similar to, would be the same as if we have a full line pool. So the line pool includes all potential paths in a network, but the number of all potential paths is so high that we have a problem which is not solvable by Gurobi anymore in reasonable sizes, because the number of paths in a network is just exponential. But that is one of the papers of Ralph, where we did a constructed by column generation on the fly. So what is the basic constraint that we look at in line planning? The basic constraint is that we define minimal and maximal frequencies for every edge in our graph. So suppose you have passengers, you have a first routing, maybe just by shortest paths, then you know approximately how many passengers are interested in using public transport on every specific edge. Then if you know how much passengers fit into a vehicle, you can somehow roughly estimate how many vehicles you would like to have along this edge, and this would be the minimal frequency. And the maximal frequency of frequency up on an edge is often due to security headways. For example, for metros, you cannot have too many. And when you have this very simple constraint where you just add up all frequencies that contain a specific edge, and it should be between this lower and this upper bound. Other constraints are certainly possible. You could have not more than k lines at some specific station. You could restrict the kilometers and a lot of other things that can be done. And I just grabbed 4 models that are rather popular in the literature. That is an easy cost model. That is a more realistic cost model. The direct travelers model is one of the earlier things, and the travel time model. And I want to talk a few slides about the cost model and the travel time model here. So the cost model can be specified easily in 2 slides. We want to minimize the costs of our line concept, and to this we have to approximate a cost for a line. That is only possible if you have a line pool where you can go through all of the lines separately and can estimate the costs. That can include some cost per kilometer and some cost per minute. And you know how long you drive and how long the line is. And then you can minimize the cost such that the lower and upper frequency constraints are satisfied. And you directly see this is a multi-covering problem, because here it's not only one. So if you only have this constraint, it's a multi-covering problem where you cannot choose 1, 0 or not, but you choose also the frequency, how often you want to have your item, and you have to cover not only one but also several times. And it is again NP hard. And here the solvability depends on the size of the line pool. Yeah.
So if you do the sum of frequency on edges, you assume customer will jump to first. How do they choose the line if you have multiple lines between the same edges?
Oh, I have often very many lines for the same edge. So that is, I have in my line pool, in the line pool which is given, I have a lot of lines, and each of the lines is a path, and many of them can cover the same edge. But I choose a selection, a subset of this line pool, such that every edge is covered with the right frequency.
So my question is, you use a linear frequency constraint. Does that imply the frequency can be additive on every edge?
Yes, the frequency is additive. I have a bus line with a frequency of 2 going along this edge, and I have another bus line with a frequency of 2 again, when I have a frequency of 4 buses per hour. So this frequency constraint is additive. We just count how many buses go over the same edge, how many vehicles. And if they are equally spaced or not is later on determined by the timetable. But that is linear.
So if the history matters, could that be put into the framework by history? I mean, if there's a road network, for example, sometimes it's much more costly to take a left turn than to go onto that same edge straight, or sometimes it's even better to do 3 right turns than to do 1 left turn or something like that. So you can imagine in rail it could also be that it's very hard to go from that line to that, and it's easier that way. So that's not compatible directly with the framework, right?
So here we've usually not, but you could go into more details. That would be routing of trains, for example. That is a very complicated process. Alone in a station, a big station, the routing of the trains through a big station is a problem by itself in some sense. You could go and boil it and detail it to have a more detailed network with every signal or every crossing point is a node. Then you could maybe do that.
Oh, I see. But that would.
But usually we have that.
Right?
But usually we work on that in a macro model more. Okay, it is NP hard again, and as I said, the complexity depends on the size of the line pool here. And then the travel time model, which is really hard to solve now, NP hard is really hard in this case, has an interesting assumption that is not only important for line planning, but also for all other planning steps, namely the behavior of the passengers. So what we want to do here in most models, in the clean way, they assume that the paths of the passengers are somehow known beforehand. But this is not really realistic, because if I, as a passenger, take a line or use public transport, depends a lot on the connection. If I have 3 changes and it's a long time, then I won't do it. But if I have a direct line, I would do it. So what passengers do is they choose a specific path, if it is short, if it has few transfers and a high frequency. And what path I take can I only determine when the line concept is fixed and not beforehand. So all these properties depend on the line concept, which is yet to be determined. So we have a kind of chicken and egg causality dilemma. Where should we start with? And the idea is that we would like to do it in the same step simultaneously. And while it is really hard for timetabling and other things, it can be done at least for line planning, at least if the line pool is not too big. And the idea on how to do it is to estimate the decision of the passengers by assuming they choose the one with the smallest perceived traveling time. That we can already estimate in the line planning stage. So what we estimate is the riding time. So on an edge, this is more or less known, how long the metro or bus would take for any edge. And we have a penalty for each transfer the passenger will have. And then we can take this one and use that to model the decision of the passengers. And to model this decision in the passengers, we need another network. So this is the public transport network, where we have stations and direct connections. And I already marked 3 lines here to show you the next step of the network, which we call change and go graph. So in the change and go graph, we model each station for each line as a different model. So we have 4 stations for the red line and also stations for the blue and the green line. And we connect the stations if they have a transfer possibility. So we have to connect the green and the red node at station S3 and the red and the blue one at the stations S1 and S4. So that is what we do here. S1, you can change transfer between red and blue, and also on S4, and with here you can change between the the red and the green line, and here between the blue and the green line. So that is the change and go graph, where we have to add also origin and destination points to allow the routing. And then in this graph, we can do the passenger routing. And including this as constraints in our model, we can do it simultaneously. So what we need are variables for the routes of the passengers. So this variable is 1 if the OD pair what wants to travel from S to T uses the activity A in our change and go graph here. So that codes just the paths in the change and go graph. And here is the decision variable if we want to have a line or not. And then we take the node arc incidence matrix of the change and go graph and get the following model. So here we minimize the travel time, sum of all travel times of all passengers. So that is if a passenger takes the edge A, and that is the number of passengers that do it, and that is the weight, how long it takes, and the number of passengers that do it. Then you can only take the edge if the corresponding line is established in the network. Otherwise, there is no edge to take. And this is the flow constraints with the node arc incidence matrix, and this is the budget constraint. And with this, you can do it simultaneously. This would be without frequencies, but you can also do it with frequencies if all vehicles have the same capacity. And this model is hard to solve. It is, even for relatively small examples, hard to solve. We now used the new Ruby version and some tricks so that we can do it with medium-sized models, but that is something that is rather new. But still, it can be done. Okay, and yeah, there are some special cases where you can solve it, but most special cases are in p-hard, and Danzig-Wolf decomposition would be an algorithmic approach. Yeah.
In this type of model, well, is it common that you consider congestion? Because if you sign a lot of passengers on a particular line...
Here we are not looking at congestions. So if you think of metro lines, there would not be a congestion, hopefully, and we have limited the upper frequencies, assuming that they are small enough that you can just use the travel times that you have. So you mean congestion if too many passengers want to board the same bus? Yeah.
Because your frequency could be dependent on
that is true.
Demand, right?
If you have a lot of passengers boarding the same bus, that is an important thing. And you have this bus, what is called, where buses get closer and closer to each other. Yes, exactly. So, but we are not modeling it here in the line planning stage. It depends on, so I mean, what we do here is European context or German context. We have rather the problem to have very empty buses and not very full ones. But if you would model the same problem in India, you would have other problems to face, definitely. What about equity for line planning? What we could do to treat all people in the same way is restrict the maximum number of transfers. It's maybe unfair if some OD passengers have a lot of transfers, others not. We could look at this perceived traveling time. It is clear that it is longer for long relations, but we also heard this morning, it would maybe be good to minimize the ratio between the individual car and public transport, to give everybody the same opportunity to use public transport. And again, here we could also improve the line concept, in particular for OD pairs with low income or which have no car possibility or no driving license or school kids. That was line planning. Now I'm getting a little bit quicker maybe with timetabling. Timetabling is the next step, and now we want to assign times to our events. And an event is the arrival or the departure of a bus or train at a station. So for every arrival and every departure, we now want to have a time. That would be the timetable. First, one important decision, the timetable could be periodic or aperiodic. The constraints are easily set. We just want to respect driving times and dwell times. And the goal in timetabling nearly always is to minimize the time passengers spend in the system, so the sum of the riding and transfer times over all passengers. Also, a new objective is to look for robustness, which is also important. And here I want to show you the third graph model which is used. So the first is the public transport network, where we just have the stations and direct connections. The second was the change and go graph, where you have the transfers. And this is another extension similar to the change and go graph, where we also have 3 lines. So we have one line which departs in some station A, drives to K-Town, Kaiserslautern, that is the English or American name for it, because we have the largest US base in Europe, very close to Kaiserslautern, and all the Americans call it K-Town then. Here you have a dwell edge where passengers can board and depart when the train starts again and drives to station E. We could have another train coming from B, passing K-Town and going to F, and another one starting in Z, passing K-Town and going to G. That is the event activity network with driving and waiting edges. And then we make it, so that would be easy for making a timetable because you have no connection between anything. But when we add transfer activities, somebody could get off here and board another train. So coming from A, going to G would be like this. And these are the transfer opportunities. And then we also might need headway. If all the trains use the same track later on, they cannot depart at the same time. So there has to be a special certain distance, which is then the headway. And now we want to add lower and upper bounds. So that is L and U for driving activities, is how long this train needs to go from some station to another one. Trains cannot fly or beam, so they have to take some time, and this is the upper bound maybe. Also for transfer edges, we have this bounds. And what we now look for is we want to assign a time to each of these nodes in the network. So it is somehow a potential problem where I add the times. And we have this lower and upper bounds for every activity. The timetable assigns a time to each of the events. And what I now want to show you is the difference between aperiodic and periodic timetables. So in an aperiodic timetable, feasibility is defined very easily. You look at the point of time here. This event is at, for example, 7:55. This event takes place at 7:45. You subtract these 2 times, and if you are within, so this is 10 minutes, obviously. 10 is between 8 and 12, so you are feasible, this is fine. This can be formulated as program. You can choose if you want to have this PI as integers like minutes or seconds or not, because the matrix is totally unimodular anyway, so they will come out nicely as integers anyway. And this problem can, in this easy form, even solved in polynomial time. Now if you, yeah? Aperiodic means there's no constraint. If you have just a long day and each arrival and departure is a node, and maybe you have 2 departures per hour, but this need not be the same in the next hour. So in 1 hour, it departs at 14:10, in the next hour, 14:17, or something like that. Now, if you have a periodic timetable, you only plan for 1 hour, and this 1 hour is then repeated all over the day, which is the usual thing in metropolitan areas. So you take the same event activity network, but the interpretation of the event is a bit different. It's not an arrival and departure of a vehicle, it's the arrival or departure of a line. And you do it for 1 hour, and then you have it for the whole day. So we have the same upper and lower bounds. And a timetable, if your period is 1 hour, then only determines the minutes. So you have only between 0 and t-1, which would be 59. You just determine the arrival is at 15 past or 25 past, and the maximum would be 59 past. Okay, so this is the variables. The network gets smaller and the variables are constrained, not just integer, but the feasibility is now not so easy to see. So again, we have to check if the feasibility, if this thing fits into this interval. So in this case, you again subtract 55 minus 45 is 10, that is fine, we are here. But here, the train would depart here at 5 minutes to the full hour and end here at 5 minutes past the full hour. You see that is also 10 minutes, but just subtracting, we have 5 minus 55 is minus 50, which is obviously not in this interval. So what you have to do is to have modulo computation. And instead of putting modulo, you can also try to add, or not try, you add some integer multiple of a period. And if you find an integer number such that plus this integer multiple falls in this interval, then the timetable is feasible. And these Z are called modulo parameter, and they make the problem hard. So that is then the very much known periodic event scheduling problem, the PESP, and originally defined by Serafini and Ukovic, where they have the modulo parameters like here. So it looks similar to the other problem, but here you have the modulo parameters, and this is an additional integer variable. The matrix is not totally unimodular anymore. It makes the problem very hard to solve. So there are some theorems about it. I already told you in the aperiodic case, we can do it polynomially if we don't have any other constraints, which in practice we would have. And for PESP, it is NP complete even to decide if a feasible solution exists, no matter if you optimize it or not. Already the feasibility problem is NP complete. There are some nice properties about cycles that can be used to design algorithms, and there's a lot of elegant theory about it, but I want to go to maybe integer programming has been done, again, also by Ralph. SAT solving has been tested. Fair heuristics, very much known as the modulo simplex or the matching approach. Yeah, I can give you many more details, but maybe not today. And coming to the equity also here, what would be equity in the stage of timetabling? We could say we want to have good waiting times at all transfers. So we don't want that some passengers have a long waiting time if they transfer, and others can have a good and a convenient transfer. We could maybe do that by minimizing the largest transfer time. Or we could try to minimize the maximum difference between the real traveling time, which we find after optimizing the timetable, compared to the lower bound traveling time, which can be easily computed by adding the lower bounds of the path. That would be maybe the fairest thing if we want to treat everybody equally. Timetabling. Now we come to the vehicle scheduling problem. As I said, that is maybe not so interesting from an equity perspective, but it is very crucial to compute the costs. And I just want to sketch how this can be done. We now have given a line plan and a timetable. And the question is, how can we serve that? We have a line plan and a timetable, and we now need to decide how many vehicles do we need such that we can serve the whole line plan. The goal is easy here. We want to minimize the costs, and the costs depend on the number of vehicles and the kilometers the vehicles have to drive. Now, what is clear is that if you have one line, then from the start to the end, it should be served by the same vehicle. If you have one line, you cannot tell the passengers, oh, now you have all to get off and take another bus. So passengers want to sit in the same line. And it would be very easy to say that every line is served by having a vehicle always going back and forth the same line, but it can be shown that you can save quite a lot of money if you allow a little bit more flexibility. So what we need to do is to define a trip, and a trip is such a basic thing that has to be served by one vehicle. I show it in an example. So here we have two lines, a blue one with a frequency of 1 and a red one with a frequency of 2. They have travel times and they have starting and ending times, not so important. But what is important is that these two lines come out with 6 trips. So we have this blue line, we have one trip where that blue line goes upwards and one trip where the blue line goes downwards. These are the 2 trips here. And since the frequency of the red line is 2, we will have 4 trips. 2 going upwards, 2 going downwards. And each of the trips comes with a start and an end station and a start and an end time. In the next step, we have to say that 2 trips are compatible. They are compatible if they can be served by the same vehicle. So assume we have a vehicle that ends its trip at one station at one time, and then it could start at this station with another trip, or maybe have an empty ride to go to another station and then use a trip. And this is all we need to know. And we can solve this vehicle scheduling in the basic form as a circulation problem in a network. And this is set up as follows. So we have the trips that we want to cover, and we just put all the trips here. Then we connect them to the depot where the buses come from and the depot where they go to. And we also have an edge from the arrival depot to the departure depot. It can be the same depot, but whatever. And then we mark which trips are compatible. So for example, after trip 1, the vehicle could go here and then serve trip T3, and then it could go here and serve trip T4 and then go to the depot. And if we now add the right numbers, we can solve the whole problem. So the costs of the trips are 0 because the trips have to be served anyway, so that is constant. We can just put them to 0. But the trips between the costs for the empty rides between the trips can have some costs. If it's the same station, the cost is 0, but if the vehicle goes to another station, we have to count the kilometers. Then we need the costs for going to the depot, and the costs per vehicle are on this backward arc. And we need to have some bounds. We need lower bounds for the trips to make sure that they are served. And we can have an upper bound here if we have a limited number of vehicles. And with this, we can find circulations for all of our vehicles and solve the problem. So this is a correct model, and it can be written down as flow problem, solvable in polynomial time if we have one depot. If we have several depots, it's getting NP hard. Then we have a multi-commodity flow problem. Equity, not so important here. It's important to take care of a budget, but the passengers do not even see the vehicle trips. So I think for the passenger, it is not a matter if you need more or less vehicles. It is maybe important for crew scheduling in the next phase, and this has been treated in the so-called rostering problem to treat drivers equally. So I have a few slides for disposition and then tariff planning, okay? Disposition, maybe I do it really quickly, is the problem what to do if you have delays. If you have delays, you have to find several decisions. So in case of a delays of trains or buses, you have to make the decision if you want to wait for transferring passengers or depart on time. And if you have two trains that would like to go on the same track, you have to decide who is going to be first. This is a picture of a disposition center in Germany, in Hanover, where you see such a person looking at a lot of screens and deciding such things. You can model this as integer program, where you have a timetable, you have variables that code the new timetable, the disposition timetable, and you have 0, 1 variables that tell you if a transfer is maintained and which train goes on which trip. And it is maybe easiest to see that again on the event activity network, which is the same as we had for timetabling. So you have now look for a disposition timetable instead of a timetable. And you have to decide for the blue transfer activities, if you leave them in the network, then the transfer is maintained and the delay propagates along this activity. Or if you take them out, then the transfer is not maintained. The passengers have to wait maybe a long time for the next train, but the delay does not propagate. And the same for the headway constraints, which can be used to decide which train is going first. You can code it as integer problem. It is NP hard. And what about equity? I would not advise to minimize the maximum delay in this case, because delays are a kind of emergency. And if you really would take care for everybody, I think many other people would suffer too. So it would be easy, for example, to maintain all transfers by shifting everything behind or to the end. But then you would end up with a large amount of delay for everybody. So sometimes in this case, I think you have to give up connections and accept that some passengers are not treated well in some sense. And this is done. So also in German railway, passengers can, instead of that, claim money back or get overnight stays if something does go completely wrong for them. But I think that is something we have to consider here. Otherwise, we would have delays everywhere, and we have too many. So we have anyway too many. It would maybe be better research to avoid spreading of delays in the same way in every region or on every line. That would be something which you could do under equity perspective, I think, that you try to give the same slack time to all of the lines, something like that. Tariff system, the last point here. Tariff planning concerns finding the prices for the passengers, and that is maybe a very crucial thing for equity. But what I do here is not to look at the income or whatever. So what I can refer about is that we looked at tariff structures. So a tariff structure could be, for example, a flat tariff. A flat tariff means that everybody pays the same. It could be a distance tariff. in the distance tariff, the price for a journey is related to the length of a journey, to the kilometers, often in a fine linear way, that the price of a journey is some fixed cost plus some price per kilometer. Or it could be a zone tariff that is popular in Germany, also in the US they exist, where you look at the number of zones you are passing and then you can read off the price. What we would have to expect from a fair tariff structure is that it satisfies two properties. I call the one the no stopover property, which means that if I split my journey into several sub-journeys and buy tickets for each of the sub-journeys, then I would not expect that I can save money with that by splitting my journey into sub-journeys. And the no elongation property says that a journey should not get cheaper if I stay longer in the bus. So that is something we would expect. And the tariff structure design problem is then to find a tariff structure that has some nice properties. So usually we have given some, in this problem, we have given some reference prices. That is, somebody decided these are the prices for every journey that I would like to have. And then we have to fit them into a zone tariff or a distance tariff or flat tariff as good as possible. That is the tariff structure design problem. There are two applications. One is if we have good reference prices and we have to realize them, then we can design the zones and the zone prices in such a way that they fit very good to the reference prices, or also in the transition of tariff systems. And the transition of tariff systems is something we did some time ago in the Saarland, that is a German state, the smallest of the German states, except of the city-states, where they had 9 different public transport companies that joined together, and they wanted to have one common tariff system. They all had different prices, and they wanted to have zone prices later on. Here you see the zones, and we designed zone prices such that all of these 9 public transport companies was happy by finding back prices which are similar to the old prices they had. And what you see here is some kind of equity we looked at. So here we graphed which of the customers had to pay more than before. And these were the red lines, and if they are bolder, then more passengers were affected. So this is a histogram where you see how many passengers from which company had to pay more or less. For example, the orange company, that was an increase of 30% for all of the passengers here. So that was a tool to discuss equity in this setting. It's, again, not always NP hard. So if you want to design a flat tariff or a fine linear distance tariff, that is easily solvable. Also, the prices can be solved rather easily. The zone tariff design problem is NP hard. And equity. So tariffs are considered as the application of equity, but in what I did in this work, I think the only thing we can do is that the reference prices should be fair, and when finding a tariff structure, it should minimize the deviations also in a fair way. But thoughts a little bit outside of these problems are rather important too. First of all, it's important to choose the correct tariff structure, and this is very interesting. I mean, for example, in a flat tariff, you have the same price to pay for everybody. So the people with short journeys, they pay for the people who do long journeys. And if it is fair or not is a question, but you should try to avoid that people with short journeys are the ones who have low income anyway, maybe. Then they would support the rich people coming from far away with the public transport. But for example, in Santiago de Chile, it's vice versa. So the rather poor people live right outside, so they benefit from a flat tariff system here. Also, if you want to do it in an equity, then the tariff system should not only depend on the journey, but also on the passengers. And this is done in most tariff systems, that you have that children have to pay less than adults, or that you have social passes or passes for refugees so that they can save money. And in Germany, it's just a relatively new development. We have now a flat tariff for all buses and all regional trains all over Germany for 59 euro per month at the moment. So if you buy that for 59 euros per month, then you can use any mode of transport except of the long distance railways just for this flat tariff. Okay, so that's where I went through the thing. dilemma. Tariff planning is missing here, no problem. And now I want to have some final remarks on equity, which I managed in the hour, that's fine. So what we have seen now in the talk is that I added some ideas on equity for each of the planning stages. And some of the things are easy to do. For example, to look only at people who maybe don't own a car. Then it would just be a change in the demand matrix, and the model need not be changed, the algorithm need not be changed. We just could concentrate on people who need it more than other people, maybe. So that would be a good direction into equity, and we could already do it now, because the models are there. It's just the demand matrix, which is an input, so that would be an easy thing. And it would be probably very interesting, maybe not from a mathematical point of view, but from an applied point of view, to see the difference in the outcome. Other things are not so easy. Other aspects are, from a mathematical part, challenging. If you want to add equity, I showed you some of the ideas also for the PASP or for line planning, that would lead to new models and probably challenging new research also in mathematics. But, and I think it is worth to look at that. But the question is, that is all on a more or less local level. And is this the thing that we really want? And I want to give you a little bit on a global perspective on a project we are just working at in Germany, which is a bit similar to Hani's project this morning, about urban mobility. So what we have given in this project is a city with some street structure and a demand matrix. So again, demand matrix is given, but to all of the region here. And the question is, or what we want to do is we want to determine the best transport modes which should be installed in our city, in our region, where we consider not only one or two, but three objectives in a multi-objective way. We look again at the traveling times or perceived traveling times of the passengers. We look at the budget, and we look also at CO2 emissions and energy as environmental aspects. So, and the questions we raise and that we would like to answer is, given such a demand structure and a city, do we need a metro? At which level is a metro worth to be established? Where in the city should we offer regular bus transportation? With which lines? Where is shared mobility? We call it ride pooling often, but not autonomous shared mobility, but shared mobility more appropriate. How many vehicles would we need? And to whom would we recommend better to use a private car, because it does not make sense to connect every small house to every other small house. So in pictures, the thing what we would like to do is the following. We have given some street network in a city or whatever, and we have a demand matrix from where to where people would like to travel. And what we would like as an outcome is something like, okay, the pink thing should be maybe a Stadtbahn, a metro line. Maybe all this brown stuff here should be regular bus transportation. Here in this area, we would offer some shared mobility, and maybe also here. And the rest of it should take private cars. Something like this would be interesting and would be nice to know for our planners what would be an optimal transport mobility system. And then, I mean, it's very differently maybe nowadays when we need to shift something. Yep.
Is there any type of research into almost like zooming a level out on this and saying, can we redesign the city to better fit like a transit system?
Right. So in case we would be able to solve that, we would then have to have some transition steps, or we could even say we do not want to get rid of a metro because rebuilding a metro is nonsense, so we would fix it if we do it for a real city. But I would also like to understand it from a theoretical point of view. If a metro would not be there, would we build it in this way? So this problem is challenging, as you probably recognize. We want to do it multimodal. So we look at metro, bus, shared mobility, and we also look at private cars. That was also why I asked you. We want to evaluate it with multiple objectives: travel times, budget, and CO2 emissions. And we also consider equilibrium constraints. So we have Tobias Haags from Germany in our group, who is working on equilibrium constraints, expert on this. And we want to do that because we want to model the behavior of the passengers in a nice way. We cannot force or do not want to force passengers to use some bus or whatever. So they should use what is best for them. And this would be modeled by equilibrium constraints, allowing us also to compute the traveling times, including traffic jams. So if everybody uses the car, it gets crowded and it gets slower. That is what we also take into consideration. So this is not easy. and we also have to use some workaround. You started with the zones. We did it a little bit different way. So we use a decomposition approach into a surrogate model, which gives a global view, and detailed models then for planning metro, buses, and shared mobility. And this works as follows. So the surrogate model does a routing, a first routing of passengers, and then sees how many passengers are on which edge. And then if there's very many, it says, okay, here metro could be appropriate. That is basically a bit more complicated. It recommends modes of transport due to the number of people who want to use a specific edge, and the detailed models then plan accordingly the public transport system. And then we compute the equilibrium routing in this new mobility system. And the result, we started with a not so crowded region in Kaiserslautern, was very demotivating for us. What happened? Everybody who can, so not school kids and so on, takes the car. So you have a question?
Yeah, just a quick question. So in this scenario, you're assuming that there's one agency managing all these?
No, yeah. So we assume that there's one transport agency, but the passengers are agents by themselves. So we have one transport agency and a lot of agents, namely every passenger is an agent. Yeah, right. So the result was, in a not so crowded version, it was not Munich or Berlin maybe, but everybody who can takes the car. And why did that happen? This happened because the budget is not enough to make public transport competitive to car transportation. Even if there's a bit more traffic jam compared with going by public transport, you have to walk to the first bus, then you take the bus, then you have to change. So it just takes longer, even if you suffer a bit of traffic jam. So we could have the capacity of the street smaller for sure, but the question is, wouldn't it be better, maybe for all of us, for the society to have not equally every line as good as possible, but to have some sufficient transport which helps for everybody. But when you pick some lines and you have some really good lines, which have a high frequency, clean buses and quick traveling time, and these are then not equal, it has only some lines, but we have some people using not the car, being happy to use the good lines, and maybe that is better for all of us to get our cities cleaner and avoid too much traffic jam. So that is the question, and this would be something which is rather not equity. So that is my question in the end, and this is my last slide then. Yeah, please.
Do you assume that you know the routes that passengers want to take? Because you need to know like the number of a specific edge that people want to use. So do you know like the specific passenger routes for every?
The routes are determined. The routes are determined in the equilibrium constraints. So we know from where to where passengers want to go, the demand, but which route they take and which mode they take. If they take the car, if they take train, metro, or bus, that is determined by the equilibrium constraints. That takes every passenger as agent, and every passenger does the thing which is best for his traveling time, or perceived traveling time. Yeah.
And that result where everyone takes a car, just to be 100% sure, that's already counting for congestion?
Yes, that includes congestion. So, but not in a very big city. In my hometown, which is not too congested, but still we thought, it would maybe be different in a very congested metropolitan area. Yeah.
Yeah, my question is about active mobility. Did you also consider cycling and electric scooters and all of those
Not
things?
at the moment. We want to include that. I'm also involved in a European project where this is the main focus, to have active modes, because that's more healthy anyway. So we, at the moment, in the first model, we did not take that into account, but it's on our agenda.
We can take one last question from Marco, and then
last slide.
If you have to redesign the whole thing, right, start from scratch, would it be fair to ask, is the demand that you're observing right now is really not the correct demand? So if you design your whole thing to meet the current observed demand, would that be a problem?
So at the moment, we take the demand that is actually here. So the sum of the demand in public transport and individual car transport, everything. We take all the demand together, and that is what we use. That demand can change, for sure. We have not taken that into account. We start with a demand matrix and let it fix. And my last slide then is, maybe we need a shift of our goals. Maybe we should consider that at least. So far, I started with this slide. Under a restricted budget, The goal was that under a restricted budget, we want to make public transport as good as possible for the given demand. But maybe we should, with good, so a bit relatively. So still we should, under a restricted budget, ensure some sufficient public transport for everybody, but then make only a small part of public transport as good as possible to be competitive. If we spread our limited budget on the whole public transport system, we can increase it a little bit, but not enough to get competitive with the car, except of big metropoles maybe. And the question is if we should more concentrate on some relations which are really good to, if that would be helpful, and keep equity goals in both approaches in mind.
Okay,
Thank you for
very
your
much.